Are you ready? Then let's go.
It's time for Maths with Mr. Thomas.
Chapter 8, lesson number 1. This is the first lesson in functions and graphs. Really though, this chapter starts with lesson 2. However, rather than just jump into everything new about functions, I thought it may be worth putting in a recap of everything that we learned in functions from higher. So, if there's anything you have forgotten, if there's anything you want to go over again, it will be worth watching this just to make sure you're 100% okay with everything before moving on to the advanced higher work on functions. So, in higher maths, this is really everything that we learned with functions, so I'm going to quickly go over each of these. Anything that you're wanting in a little more detail though, or you're wanting more examples with, look back to the higher videos. So, starting off with notation. So a set is a collection of items with a common property, such as your fingers on the end of your hand. These items are known as elements or members. So the elements or members of your fingers would be the index finger, your middle finger, your ring finger, your pinky. So sets are written with these funky curly brackets, and each element or member is separated by a comma, such as this. Ba-ding, ba-ding, ba-ding. And the 3 dots on the end means that the set is infinite. It would go on and on and on forever. So you can write different numbers. You can put numbers in the following sets. So the numbers 1, 2, 3, 4 and so on, they are your natural numbers, capital N. Whole numbers are the exact same, but you also include 0. A positive or negative whole number is known as an integer, Z. And the Z is from the German word that means numbers. That is why we use a capital Z. Q is a rational number. Q is for quotient. It's what you get when you divide one number by another. So really, a rational number is a number that can be written as a fraction, such as 4. You can write as 4 over 1, or 0.7. That's the same as 7 over 10. Or the negative 0.125. You can write that again as a fraction, so it's a rational number. And every other number is known as a real number. In advanced higher, we will, in Unit 3, move on to look at numbers that are not real, such as the square root of a negative. You can't get that until you look at imaginary numbers or complex numbers, which we'll get to in Unit 3. This symbol, this little e, means belongs to, and you can use it to show that a number belongs to a particular set. So you can say here 7 belongs to W. In other words, 7 is a whole number, you know that. But 0.4 does not belong to Z. So 0.4 is not an integer. It's not a positive or negative whole number. If you have x belongs to w, it means that the number you have has to be a whole number and its x is less than 4. So in other words, the whole numbers that are less than 4 would be 0, 1, 2, 3. If you have x belongs to z, then it means x is going to be an integer, and if x is bigger than or equal to negative 7, then you could have negative 7 or every whole number above that, and the 3 dots, it would just keep on going. If x belongs to r, then you can really have any number, but x squared equals negative 9. However, you know there's no number that would square to give negative 9. You cannot pick a real number. For that, you'd be moving on to look at imaginary numbers. But it's not looking for imaginary numbers, it's looking for real numbers, numbers that do exist. And there are none that would square to give negative 9. Therefore, you have no numbers in the brackets, and it is known as an empty set. Woo. So moving on to functions. What is a function? I always think of a function like a number machine, like this one here. Beep, 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 boop, boop, beep, boop, boop. And with that, then you put a number into that, something happens to it, beep, beep, boop, boop, beep, boop, boop, beep, boop, boop, and you get something out. So there's an input which is known as a domain, a process where something happens, and you get an output. And the function shows us how the domain, the input, links to one and only one member of the range. And you write functions like f of x. You can also have g of x, h of x, k of x, and so on. It doesn't always have to be f. There are three different ways to write a function. You can write them as an equation. So you could have something like this. F of x equals x squared plus 3x. You have your domain, so you have the numbers that you're going to put into this function. So if we put in -3, well, we would replace the x with -3 in the left. So we do the same in the right. So we'd have -3 squared plus 3 times -3. And you get out your range, the result. So you get out 0 if you put in -3, if you put in -2, you get out -2. Keep on going, put in all these numbers in the domain, and the answers you get, well, you've got a -2, you've got 2 of them, you've got a couple of zeros as well, and you've got a 4. So you've got -2, 0, and 4, and that is your range. As well as an equation, you could also use an arrow diagram. So in this yellow oval shape here, you have your domain. This is the numbers you are putting into your function. The range, you would calculate that, and you draw your arrows. It's your arrow diagram. So if you put in -3, you get out 0. If you put in -2, you get -2. -1, you get -2. So you're drawing the arrows to show that. However, just make sure that you check. Each member of the domain should link to one and only one member of the range, which they do. -3 only links to 0. -2 only links to -2. -1 only links to -2, and so on. You can also graph in order to show a function. So using those results that we just had there for the arrow diagram, if you put in -3, you get out 0. So you're showing that with the graph. X value is -3, Y value is 0. If you put in -2, you ended up getting out -2. So the X value is -2, the Y value was -2. So you're showing each of those points. Notice how you're just showing the points. What we had for the domain was -3, -2, -1, and so on. So we're only interested in the Y value at those points. We would not have that solid curve between them because we're not interested when X is -2.9 or -2.8 and so on. It's only these ones we have. If we did have it though with X between -3 and 1, we would then have a curve, and we would be showing every single point along that line between -3 and -1. Again, each member of the domain links to one and only one member of the range. So in other words, every single X value links to only one Y value. So you can see here when X is -3, that's the only Y value. When X is -2, this here, this red dot, that's the only Y value. When it's -1, again, that red dot, that's the only Y value. So we're fine. Would the following graphs illustrate functions? Well, yes, this one would, because no matter which X value you pick, if you go up to your graph, well, there's only one point on the graph. It's just that point there. If you pick this point, if you go up to the graph, again, there's only one value. Pick this point, there's only one value. Really, no matter where you pick an X value, there's only one Y value. With this one here, again, you go up to the graph, there's only one Y value. If you pick it here, there's only one Y value. Do it there, again, there's only one Y value. So these would both be functions. However, if you pick this point here and you go up to your graph, you will see that there are two Y values. It could either be that one or that one. Mamma mia! Which means that is not going to illustrate a function. Restrictions on the domain. So you're looking at when it's possibly undefined. And a function will be undefined for certain values of X. And usually it's because you cannot take the square root of a negative and you cannot divide by 0. So a couple of examples here. If you've got your function f of x equals the square root of x take away 3, you would say it's undefined when? Well, it's going to be undefined when the x take away 3 will be less than 0, because then you would have the square root of a negative. So if x take away 3 was less than 0, if you add 3 to both sides, then you would say x would be less than 3. That is what would make your function undefined. And it makes it undefined because that would give you a negative. You cannot get the square root of a negative. Yeah! So what values of x could you have? Well, if it's going to be undefined when x is less than 3, then it means it will be defined. You could have an answer when x would be bigger than 3. And make sure you include as well, or equal. If it was equal to 3, you would have 3 take away 3 is 0. You can get the square root of 0, that's just 0. So it's going to be when x is bigger than or equal to 3. That's what you could have. That would be the values of x, your domain. With this example, f of x equals 1 over x bracket x plus 5. Again, think it's undefined when? Well, it's going to be undefined when you get the square root of a negative, well, there's no square root signs. Or, what's the other one, Sahana? Good, when you try to divide by 0. You can't divide by 0. High five, Sahana. So with this one here, you will say it's undefined when you do know the denominator is 0. So you'd have an x times the x plus 5 would equal 0. Split that up, so either x is 0 or x add 5 is 0. Keep an x as 0, or if you subtract 5 from both sides, x would equal negative 5. These are the two values that would make the denominator equal 0. So in other words, it's undefined. You cannot have it when x equals 0 or x equals negative 5. That would give you a 0 in the bottom, and you can't divide by that. No. So what values could you have? What could you have for the domain? Well, really, you could have any other number at all. So you would say x belongs to R. X is going to be a real number, but it can't be 0 or negative 5. You can pick any other numbers you like. After that, we look at composite functions. A composite function is basically a function that combines more than one function. So a lot of the time in higher you had maybe f of x, but you were also given g of x as well, and you were asked to work out f of g of x, or g of f of x, or f of x, or g of x, and so on. So if you want to work out f of g of x, what you're really doing is you're thinking start at the middle with g of x. G of x is equal to x squared, so you're replacing g of x with x squared. So you'd have the f of x squared. It means then in function f, you're replacing x with x squared. So everywhere you see an x here, you replace it with x squared. So you'd end up with x squared, take away 2. G of f of x, you're just doing the same thing there. Start with the middle with what f of x is equal to. It's equal to x take away 2. So replace that, so you want g of x take away 2, and then sub x take away 2 in function g in place of x. So instead of x squared, you'd have x take away 2, all squared. And multiply the brackets and work that out. Yeah. After that, we looked at inverse functions. So what is an inverse function? Well, you know a function, first of all, is where each element in A corresponds to one element in B. A function that allows us to go back the way from B to A is known as an inverse function, and there must be one-to-one correspondence between the domain and the range. So you can see here every element in A links to just one element in B. So negative 2 links to 4, negative 1 links to 1, 0 just links to 0, and 1 just links to 1. So that's fine, it is a function. But going back the way, well, 0 only links to 0, so that's fine. The 4 just links to negative 2, so that's fine. But the 1, dun dun dun, it links to negative 1 and 1. There is not one-to-one correspondence, so an inverse will not exist. However, with this one here, with g of x equals 2x take away 3, you can see that every element in A links to just one in B. But you've also got it going back the way as well. Every element in B just links to one in A. So negative 7 just links to negative 2, negative 5 just to negative 1, and so on. Because there is one-to-one correspondence, it means an inverse exists. Woo! Inverse! Yeah! How do you work it out? Well, let's look at this one here. Let's say you've got the function f of x equals 5x. You know, to go from A to B, you're multiplying by 5. That is what you would do with your number machine. Beep, beep, boop, beep, 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 boop, boop. But to go back the way, how do you then reverse that? What's the opposite of times by 5? Divide by 5. Perfect. You would divide by 5. The way you write inverse x, the inverse function is f to the minus 1 of x. And if you're dividing by 5, well, you're taking a fifth of x. So here you would say the inverse function, f to the minus 1 of x, equals 1/5 of x. Obviously though, this example is dead easy. If it's a bit harder, sometimes you've got to think about changing the subject of a formula. So if you had to work out the inverse of 4x plus 3, what you really want to do is you change f of x to y. So instead of f of x equals, you would say y equals. What you then do is you change the subject of the formula to x. The way you do that is think about what's happening to the x here. With x, you're multiplying by 4. So I'm multiplying, that's what I'm thinking, and then I'm adding on 3. To undo that, I want to go back the way, and I want to do the opposite. So the opposite of add would be subtract. So I would subtract that 3 first of all. So subtract 3 from both sides, or move the 3 over and then take away. So you've got y take away 3 equals 4x. After that, well, you were multiplying. What's the opposite to multiply? Well, it's divide. So you would then divide by the 4. I'm writing it back to front first of all, then dividing by 4. So that is me. I've changed the subject of the formula. Once you do that, you swap the y with x. So instead of y take away 3 over 4, you've got x take away 3 over 4. And you also swap the x for f to the minus 1 of x. So therefore you will say then that f to the minus 1 of x, the inverse function, is equal to x take away 3 over 4. So that is how you'd find the inverse. We then looked at graphs of inverse functions with these 3 here. 1, 2, 3. What do you notice about them? If you've got f of x and its inverse a half x, or if you've got x plus 5 and its inverse x take away 5, or the 3x plus 5 and then a third of x take away 5. What do you notice? Perfect. Well done. High five, Alan. With this, you can reflect f of x in the line y equals x, and you end up with the inverse. So to graph the inverse, all you really want to do is reflect y equals f of x in the line y equals x. So you can see here you've got f of x equals 2x. If you reflect that over this line y equals x, in other words the point 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, if you join the line up, or the line at 45 degrees, and reflect over, that will be your inverse. Notice if you have the point 2, 4, in order to work out what the point would be on the inverse, all you do is you swap the x and the y around. So 2, 4 would become 4, 2. Or if you have negative 10, negative 5, swap the x and the y's, so you'd have negative 5, negative 10. So that's how you can easily find out what the point would be. We then looked at exponential functions. That is something that we've also touched on with advanced higher already. If you have f of x equals a to the power of x, that is known as an exponential function with base a. The base is just what's at the bottom, and the index will be x. So a is not equal to 1, and a would be bigger than 0. So with this exponential, f of x equals 2 to the power of x. Really, if you're graphing that, that is what you get. You end up with something that starts off quite shallow and then gets steeper and steeper and steeper and then dramatically steeper. You end up with something that goes like that. Really, your exponential function will always pass through the point 0, 1 and 1a. A is the base. So here, because you've got base 2, it'll pass through the point 1, 2. What is the inverse of an exponential function called? Say it. Perfect. It is your log function. So a logarithmic function is looking like this. Y equals log base a of x, read as log base a of x. And really, since it's the inverse of an exponential, you can easily graph it. So your exponential function, it starts, I always think about it looking like an e. If you write e for exponential, well, when you start writing an e, you go up like that. So that is what your exponential looks like. And really, your inverse is the log graph, and your log graph will look like that. Really, you're just reflecting it in this line y equals x. Because your exponential function always passes through the point 0, 1, your log graph will always pass through 1, 0. And because your exponential passes through 1a, then your log graph will pass through a, 1. And again, a is whatever the base is. So here you've got log base 2x, so you know it's going to pass through 2, 1. The last part with functions from higher was the graph transformation, Olivia's favourite. So, with the graph transformations, there are 6. We have y equals f of x plus or minus a, y equals f of, in brackets, x plus or minus a, y equals negative f of negative x, and then k of f of x, and f of k, x. A quick summary of them all. If you have y equals f of x plus or minus a, what does the plus or minus do? Move it up or down. Brilliant, it just moves it up or down. So if you have f of x plus 5, well, it's going to move every single point up 5. It's just going to move it up. If you have y equals f of x take away 7, it'll move every point down 7. Brilliant, it'll just go down 7. So if it's plus, it moves it up, negative moves it down. If it was in brackets, y equals f of x plus or minus a, what does that do? Left or right? Perfect, it's going to shift it to the left or the right. If you have a plus, if you have a positive, it doesn't move it in the positive direction, it moves it in the negative direction. So you can see here you've got f of x plus a, so that plus is going to move it in your negative direction. If you have y equals f of x take away 3, well, instead of going down 3 to the left, it would move up 3 to the right. So be careful with the signs there. Plus moves it in the negative direction, negative moves it in the positive. You also get the negative as well thrown in, so you can have the negative f of x or f of negative x. The way I always think about it is if the negative comes first, so if it doesn't come second, if it doesn't come after what you start writing, if it's first, well, if you think about x and y, x is first. So that is going to flip the graph in your x-axis. So instead of if you had y equals f of x looking like that, it'll flip it in your x-axis, so it'll reflect it down. Down, down. If you have f of negative x, that will flip it over your y-axis. So if this here was y equals f of x, that's going to flip it over, so this point here will reflect over to here. This point here will reflect over here, this point here reflects over here. You get the idea. Really, your y-axis will be your line of symmetry. If you have y equals k f of x, I always think about your trig graphs for this. So if you had your y equals sine x, if you had 2 sine x, hopefully you remember that's going to stretch the graph. It's going to stretch it up 2. If you had 3 sine x, well, that will stretch it up. So instead of a maximum at 1, it would go up to 3. Instead of being down at negative 1, it would go down to negative 3. So really, this value is going to stretch your graph. The same if you had y equals half f of x, well, that would compress it. So instead of going up to, say, 1, it would only go up to a half. So it's going to stretch it or compress it vertically. And the last one, if you have y equals f of k x, that is again going to stretch or compress the graph, but horizontally. Again, think of the trig graph. If you have y equals sine x, if you have a number in front of the x, so say sine 2x, well, that means you're going to have 2 sine graphs between 0 and 360. So really, if you have a number there that's going to be bigger than 1, it's going to compress the graph. Really, you're halving the value of x. So instead of have a maximum at, say, 90, well, if it was f of 2x, well, it would only be at 45 there. If you have a fraction in there, well, that is going to stretch the graph. So it'll stretch and compress horizontally. That is really your 6 graph transformations. You need to be familiar with them. Use this table. If you need to go back and practice any of these, you're best to go back to the workbooks from higher. There is no exercise on this in the advanced higher workbook that I have given you. It starts with 8.2 because that is really where the advanced higher starts course. Advanced higher course starts. This is really just a recap of everything that you should already know. If you feel confident with that, feel free to move on to the next lesson. Best of luck. Bye.